the seminar of Professor Arezzo. Professor Alessandro Arezzo is currently associated with ICTP at Trieste, Italy, and he's the head of mathematical section there. And today he's going to present us this seminar on the title Canonical Riemannian Matrix on Algebraic Manifolds. So I hope there will be lots of algebra as well as differential geometry stuff. Over to you, Professor Arezzo.
Well, thank you very lot. Thanks a lot, Imran. It's a great pleasure to get in touch with all of you. Now we are officially partners, so as a new affiliated center of ICTP. And of course, there is a long tradition of collaboration between ICTP and your community. So I'm really very happy and very grateful for this invitation. Hopefully, I will meet you in Trieste, and I would also be coming someday soon to Lahore. So just to also, in fact, in this spirit, I mean, to start opening up our lines of research, to tell each other what do we do. I would like to talk to you about a class of problems. In fact, not even just a single one, but that it has been keeping me busy for the past more or less 20 years. So the basic question, in fact, sorry, there seem to be okay. The basic question that a differential geometer faces is given a space, given a manifold, which is the best metric that you can put on it. Now, this is a very old way of phrasing one of the central problems. I think it's usually referred as René Thom's dream in many books. And the idea is, of course, that a compact Riemannian manifold, a compact manifold has an infinite dimensional space of Riemannian metrics. But hopefully, by picking the best one, there should be one metric we should remember more about the geometry and the topology of the manifold. Now, in fact, actually, in my talk, I will always restrict myself to the special class of manifolds, so compact and complex, even though, at least at the beginning, whatever I say, it's good also in the real case. Now, sorry, it seems to be stuck. Oh, I don't know, I seem to be having, okay. So the first problem is, of course, making the problem more mathematical. So what does it mean to be the best? Okay, I cannot scroll properly. I cannot move forward, sorry. Can you, is there, in fact, I cannot stop sharing.
You can't stop sharing?
No, it seems completely stuck now.
We can see the next part of the slide. Okay, well, let me just close this share.
I seem to be stuck.
Okay, maybe let me how it is. Stop sharing.
Maybe you unshare or stop sharing and then again share the screen.
Yeah, but I cannot. So if somebody stop, I mean,
let me just open it. Let me just stop this sharing.
Sorry about this. Never happened.
No issues. This is quite usual with it.
Okay, so let me try again. Let's see if
yeah.
Let's see if it's going to work a bit better. Okay,
yeah,
now
it works. It works.
Okay, so what does it mean the best? Because that's really the problem. Now there are many possible definitions, and in fact, actually, you could pick one of these lines and follow the line, and it's not clear. I mean, in the case of complex manifold, one of the little miracles that happens is that actually whichever line you take, you will end up studying the same problem. So first of all, the best, in order to be the best, it has to be unique. So given a space, you need to prove, first of all, some kind of uniqueness theorem for the type of metrics you want to study. Now, if you are a geometer, you like isometries. So one way to say the best would be to say, well, it should have the largest possible group of isometries that a space can admit. No, and now I'm stuck again. No, sorry, it doesn't work.
Imran, you can
Now
do the
try.
same
Now
thing
try.
again. Yeah.
Yeah. Try again.
And again, I cannot even stop sharing.
It is already stopped sharing.
Yeah,
Nothing is showing in you.
Look, let me, is it okay? I mean, let's see if I continue without making, if I continue like this, do you see it well anyway?
Yeah.
And maybe
Yeah. We can see.
I avoid
Yeah.
I avoid the scrolling. Okay.
Full screen. Yeah. Okay.
So, okay, if you are a geometer, you like isometry, so you would like this. Think, for example, of the problem of this problem on a sphere, on a topological or a differentiable sphere. So then, of course, what you have in mind is that you would like to find the round metric, so the largest possible isometries. Another point of view could be saying, well, I would like the curvature of this metric to be as constant as possible. An analyst would probably tell you, well, I can define many natural functionals on the space of Riemannian metrics over a space, over a manifold. So the more natural the functional, the best should be the metric. The better should be the metric. But then, of course, you don't want to study an empty geometry. So, in fact, this is the problem of my talk. They also need to exist, which is, in fact, a highly non-trivial problem. Now, what do you hope? Well, we all hope, I mean, differential geometers hope to have, in any dimension, a theorem like this. So in the case of space two-dimensional, so compact surfaces, you would, I mean, there is a classical theorem proved by many people more or less at the same time at the end of the 19th century, which says that on any compact Riemann surface, there exists a unique metric of constant Gaussian curvature. Now, there are many comments that one can make about this theorem. First of all, well, unique, first of all, needs to be explained because it's really not unique, but it's unique up to some kind of transformation. Because if you, in fact, we are looking for isometries, so the metric should be up to something. But that's the best you can hope. The second, but more important comment is that actually in dimension 2, all curvatures are the same, essentially. I mean, they are all multiples of the same function, which is called the Gauss curvature of a surface. So this theorem, in fact, of course, as you all know, generated the famous trichotomy in geometry about positive curvature, which is in dimension 2 is the case of the sphere, zero flat geometry. Now, since I'm requiring compactness, I cannot say Euclidean, but I should say the flat torus. While in negative geometry, of course, in negative curvature, we have the hyperbolic geometries. So as I said, our dream would be to have a slice like this in higher dimension. Now, we all know that this is an extremely sophisticated problem, even in real dimension 3. So the topic of my research and my talk today is to restrict myself to a special class of metrics, which are called Keller metrics. Now, what are Keller metrics? Now, if your underlying manifold is actually complex, it means it has an operator J, which has the property that J on the tangent bundle, which has J squared equal to minus the identity, is like the multiplication by I on the tangent space. So the first requirement about compatibility between complex structure and metric is to require that actually this operation, the multiplication by I, if you want to think about it in this way, it's correct, should be an isometry. So these kind of metrics are called Hermitian. But then you would like to impose something a bit stronger about the compatibility. And that's usually, and that's what I wrote 2 lines below. So it's this definition. So you can also require that your metric has the property that the multiplication by I, this J operator, the complex structure operator, is actually parallel with respect to the Levi-Civita connection. So in this sense, in some sense, the complex structure is uniformly distributed on your space. Just for language, people doing Keller geometry like myself tend to confuse the metric G, which is usually named G, with the associated 2 form, which is called omega, which is obtained by basically by composition between G and J. This is a typical trick to pass from symmetric tensor to skew symmetric tensors. So, but sometimes you will hear in my language, I will say omega is a metric, which actually omega is not a metric, is a skew symmetric form, but that's what it means. Now, Keller geometry is very special. In fact, even the founding fathers studied this type of geometry because actually in their language, because of their simplicity about computations about the Riemann tensor. So if you are a differential geometry, if you have ever tried to compute once in your life the Riemann tensor of a Riemannian metric, you get a bit discouraged. I mean, these are very unfriendly computations that one needs to do. You need to compute the Christoffel symbols and so on. Now, in Keller geometry, all these computations become much, much simpler. And in fact, let me underline the Ricci curvature. So the formula for computing the Ricci curvature in local coordinates is in fact a very special accident of Keller geometry. So the fact that the components of the Ricci tensor are actually the complex hash of a function, and this function is log of the volume form. This actually is one of the critical accidents in Keller geometry. But having said all this, I mean, this tells you a little bit what Keller metrics are, but the most important thing is, do they exist? Now, as far as this talk is concerned, let me just tell you that, first of all, you can build by hand a complex, a Keller metric on the complex projective space. And then it's actually quite simple observation to prove that if you take a holomorphic submanifold of a Keller space, this is still Keller. I mean, the induced metric is Keller again. So if you interpret these 2 remarks simultaneously, what it means that every algebraic manifold, so an algebraic variety is by definition something which sits inside a complex projective space. So every algebraic variety has a Keller metric. So you might think of Keller geometry as the differential geometric version of algebraic geometry. So every time you have an algebraic manifold, you can actually study it by Riemannian means using a Keller metrics. It's not true the opposite. There are more Keller spaces than algebraic varieties, but
Professor Arezzo, yeah.
yes. Am I muted? No, can you hear me?
Yeah, we can hear you.
Okay. So what do we know about existence of metrics of constant curvature? Now, the problem, as I mentioned when I showed you the slicing in real dimension 2, there are many curvatures. That's the beauty and the problem of differential geometry. So there is the Riemann tensor. If the Riemann tensor, of course, contains all the possible curvature informations. But if you say which compact manifolds have a Riemannian metric with constant Riemann tensor, well, you go back again to the beginning of the 20th century, and Cartan proved that there are only a finite number. So these are not, so the notion of constant Riemann tensor is very restrictive on the type of space that you can study. If you also impose the Keller condition on top of it, of course, you are restricted even more. So among Cartan spaces, in fact, if I remember, only 6 or 7 have a Riemann constant Keller metric. So the idea in differential geometry is that, okay, the Riemann tensor is too strong. So let's relax the condition a little bit. Let's go to sectional curvature. But if you ask which are the Riemannians, which spaces have a metric of constant sectional curvature, then actually you are at the birth of Riemannian geometry. This was proved by Riemann himself. And Riemann proved that only the quotients of model geometry, so you take the sphere, the Euclidean space, or the hyperbolic space, only these has metrics of constant sectional curvature. And in fact, again, if you impose the Keller condition, even less. And in fact, even less also in terms of hypotheses are required to get the same conclusion. So again, remember that our dream is to provide possibly, I mean, if you want to be optimistic, the largest possible number of Riemannian manifolds with the best metric. So we are not happy about this type of theorems. But then again, you relax sectional, you go to Ricci curvature. What does it mean to have constant Ricci curvature? Well, these are the famous Einstein equations. They were invented by Einstein, essentially. And that's, of course, a huge problem. So if you ask me, which are the spaces, which compact manifold has an Einstein metric? Well, this is a huge problem. It's a beautiful, huge problem. We know very little. I mean, if think for example of all the quest for the Poincaré conjecture, I mean, of the past 20 years, Hamilton, Perelsman, and so on. We know a bit, we understand better the situation in the Keller-Einstein case. So if we also impose that the metric is Keller, then thanks to the work of Aubin Yao of the 70s, and then the work of many people, especially Tian, Chen Donaldson, Soon, and so on. So in the negative or zero functional class case, we have a complete picture thanks to Aubin Yao. But in the positive case, we have a very nice conceptual theorem relating the existence of a Keller-Einstein metric with what is called K-stability. Yet the question of which manifolds are indeed K-stable is still not completely solved. But okay, but we start having some understanding, but the moral is that there are very few spaces have a Keller-Einstein metric. So again, let's go down another floor. Out of the Ricci tensor, we take the scalar curvature. So finally, we have contracted all possible indices from the Riemann tensor, and we are left only with a function, a scalar function. And here, there is the key difference between real and complex geometry. Because in real geometry, one of the most beautiful theorems in Riemannian geometry, in my opinion, is chain solutions of the Yamabe problem. So, which tells you that if you take, in fact, any compact manifold with any Riemannian metric, you can actually find a conformal change of this metric. So you can multiply your metric with a positive function and make it constant scalar curvature. It's really beautiful. In some sense, so this is saying there are no obstruction on the space itself. And in fact, every space has many, because in fact, in every conformal class of metrics, there is the one constant scalar curvature metric. While if you impose that the metric should be Keller, well, then there is a problem. There is a problem which, I mean, can be described in many ways, but let me tell you this way. So I would like to convince you now that not every space, not every Keller manifold has a Keller metric of constant scalar curvature. This is an idea which goes back to the beginning of the 80s, or 1980s, by Akito Futaki. So he defined a very interesting number. It is actually a number. So on your manifold, you take a Riemannian metric and you take a holomorphic vector field X. So you define f of xg to be the integral of what? So X is a vector field, so it acts on functions by taking derivatives. So which function do you pick? Well, if you look at the scalar curvature, so remember, we are starting with a random metric G, so presumably not with any particular Riemannian property. If you take the scalar curvature minus its mean, Well, any function with zero mean on a compact manifold is the Laplacian of something. So let's call this something H. It's usually called the Ricci potential. Now, with this H, you go back and you define f to be the integral of basically the derivative in the x direction of the Ricci potential integrated over the manifold. Okay, there are, of course, good reasons why to take this, but in terms of our problem, notice that if by incredible luck, your random matrix G was already a metric of constant scalar curvature, then you see that S minus its mean would be 0. That means that H would be a constant. And then, of course, any vector field differentiate a constant to give 0. So notice that this number automatically gives 0. Okay. What is more difficult to prove, but it's crucial in this theory, is that actually this is more than a number. This is what is called the character of the Lie algebra. But in particular, this does not depend on the metric G itself, but it depends only on the Keller class of the metric. What does it mean? It means that if I take another Keller metric which represents the same cohomology class, in the sense that the associated two forms omega are cohomologous, then actually you get the same number. Now, this is quite delicate to prove with this definition, but actually Donaldson gave at the beginning of this century a completely different interpretation of this number that I would like to tell you. The idea, in fact, actually is much more general because the way he defines these numbers can apply also in the case of singular spaces, so I don't need smoothness. And more generally, I don't need even a holomorphic vector field, but just a one-parameter subgroup of the automorphism, like this row from C star to the automorphism. Okay, so if you have this situation, so you have, but you can, if you want, you can still think of a complex manifold, Keller, an algebraic variety, an algebraic manifold with a holomorphic vector field. Then what you do, if you are working in the Keller class, which is actually given by the furniture class of a line bundle, which it's not always true, but let's say it's the algebraic case, it's the polarized case, then actually you can go and look at two numbers. First of all, the simplest is you look at the dimension of the space of holomorphic sections of the line bundle where your metric should sit, but you keep on taking powers and powers. So you take L, L square, L cube, L to the 4, L to the 5, and these numbers, I mean, the dimension of the space of holomorphic section will change, and you know that asymptotically it behaves like this. It's basically a polynomial of degree n, where n is the complex dimension of your manifold. So there are these numbers d0 m to the n, d1 m to the n minus 1, and so on. This is a simple application of Riemann-Roch. You can also look at another number, which is the weight of the C-star action on the top power. And again, you do this for every power, and you get another bunch of numbers, A0, A1. I mean, the fact that this grows like this polynomial, it's again a version of the equivariant version of the Riemann-Roch theorem. And now, out of these numbers, we need only the first two for every polynomial. Donaldson defined this number, A0 D1 divided by D0 squared minus A1 over D0. And then he proved that this number actually coincides with the Futaki invariant, the one above, every time it makes sense to compare them, every time the manifold is smooth, every time rho corresponds to a holomorphic vector field, and so on. And notice, one of the beauty of this theorem is, of course, the fact that in Donaldson's definition of the Futaki invariant, you don't need to pick any metric. It's a purely algebraic construction. So the fact that actually the Futaki invariant does not depend on the Keller class, it's very transparent from Donaldson's definition. Of course, we are putting the problem somewhere else. The problem is to prove that these two numbers are actually the same. Okay, so, but then you have we have a number that, in fact, we noticed is 0 if there is a metric of constant scalar curvature. But then now I don't do it for you in this talk, but believe me, it's a very simple exercise to go and compute this number in few cases. And basically, if you take the random algebraic variety, you will not get zero. For example, I mean, you can take even blow-ups of Pn and so on. So the problem is, I mean, the moral out of this is that, of course, there are very few, I mean, you expect an abstraction, which I recall you, sets the difference between real and complex geometry. So in the real geometry, there was no abstraction. In complex geometry, there is an abstraction. And so the problem is to understand the nature of this. So the question of which algebraic varieties have a Kähler metric of constant scalar curvature is much more subtle than what you could have expected from before. So you turn to a different method. You say, well, okay, but come on. Every problem in Riemannian geometry, if you are sufficiently good, you can translate it into a problem in analysis. I mean, so the constant scalar curvature equation, how does it look like? And let's try to solve it analytically as we were kind of analysts. Now, the problem is you get discouraged immediately, because if you write down what it means, so to write down this equation, you start with a background metric omega 0, and you try to change this metric in order to make it of constant scalar curvature. Then you can write down the equation, and the equation is really horrible. It escapes essentially all known techniques about existence, uniqueness, and so on, if you study it only purely from analytic methods. It is actually interesting to compare this with the standard Kähler-Einstein, with a more familiar Kähler-Einstein problem. So what do I mean by that? If you, instead of attacking the problem of constant scalar curvature, you attack the problem of constant Ricci curvature. So if you study the Kähler-Einstein equations, you could linearize the two equations that you get. And now, if you linearize the Einstein equation, you know that, in fact, the linearized operator that you end up studying is the usual Laplacian, is Laplacian of the function. While in the scalar curvature equation, you get this kind of delicate expression here. So you see, so Laplacian squared minus, it's a fourth order operator because the equation passes from 2 to fourth order. And then it has also very high, kind of an extra term. So this is in fact called the Lichnerowitz operator. And I want just to tell you about this. There is a classical theorem by Lichnerowitz who actually proved that the kernel of this operator, in fact, corresponds in one-to-one correspondence to the space of holomorphic vector fields. So holomorphic, so of course, if you do analysis, what you hope is to work with invertible operators, so operators without kernel. So the bigger the kernel, the more difficult the problem should be. And here the kernel corresponds to the space of holomorphic vector fields, which I remind you, I mean, in general, it means the more symmetric the manifold is in terms of complex automorphism, the more difficult this problem is. So that's one approach. So you say, okay, I take the equation and I throw it in the bin because I will never be able to solve this problem explicitly. So people have invented another method to attack kind of an analytic problem, which is usually referred to as the variational approach. So what does it mean? Which actually connects to my first slide. So since we were asking our metric to be the best, and among the requirement of being the best, there was to be the critical point of a natural functional. Well, let's go back to this idea and let's study. So the constant scalar curvature is the critical point of which functional? Well, of course, said in this way, the question is a bit ill-posed because there are many functionals, of course, that have the same critical points. But for various reasons, I mean, ranging from the symplectic geometry behind all this story or other things, the right functional to look at is what is called the Mabuchi K energy, which I wrote here, but don't be scared. I mean, I wrote it here just for convincing you that it's a really complicated analytic. It has a really complicated analytic expression. On the other hand, now I have to, at this, in one talk, I really have to ask you to believe me that this is the right functional to study. But what is the idea behind the variational approach? The idea behind the variational approach is that to prove that that your problem has a solution, if your solution is a critical point of a functional, you would like to prove that your functional is coercive, as is said in the PDE language. Actually, in this language, it turned out to be more popular, the word proper, in the sense that if you go to infinity on the space of functions, your functional actually grows, let's say, at least linearly. Okay, so this means that your critical point, if it exists on a compact region of functions of the domain of the functional, and then you could start applying regularity theory to prove the regularity of the critical point. This is called properness in this language. More common is the word coercivity. Now, this gave rise to a very sophisticated analytic problem, because now I'm simplifying, of course, the story, because now, from the way I told you, it is very natural to think that there should be a theorem saying there exists a constant scalar curvature metric if and only if the Mambucci energy is proper or is coercive. And this is indeed true, but it took more than 20 years for having a complete proof of this theorem, because there are really many analytic subtleties behind this story. And this was actually proved by Tian and Darvas-Rubinstein in the case of Keller-Einstein metrics. And then in one direction, Berman, Darvas, Lu, they proved the existence of the critical point implies properness, while Cheng very recently, well, 3 years ago, proved the opposite direction. So now this kind of natural tool, so this is a natural, becomes a very strong and natural tool to prove the existence of, if you manage to prove properness of this function. Okay. Okay, so this ends the first half of my talk. So let's try to summarize what have we learned. First of all, we do not expect too many algebraic manifolds to have a constant scalar curvature metric. So, and this is already in some sense a problem, in the sense we knew that there were very few Keller-Einstein. We relaxed the Keller-Einstein condition to constant scalar curvature, hoping to get a large number, but then actually the problem is that we know that we are not going to get a huge number. I mean, there will be a larger number of constant scalar. So this leaves another problem that I'm not touching in this seminar, but I would like to advertise, in the sense that for all spaces for which there is no constant scalar curvature metric, maybe the best metric is something else. And there have been important proposals on this, on what should be the best metric in this situation. The most famous one is due to Calabi, who proposed the notion of extremal metrics, but this will take us to a different story, and I'm not going to touch this. Then what else? I hope I convinced you. It's good to have strong analysts as friends, but in this particular situation, you cannot hope to just knock the door of your colleague next door and saying, you are very good in PDEs. Could you please help me to prove this the existence of these metrics by solving the PDE? I mean, there is no way that this is really too special for analysts to solve it directly. It has to be a mixture of geometry and PDEs, so that the underlying geometry has to come in to give solutions. So in general, the question is completely open. So I hope among you there are young, strong. In general, I can tell you more or less, I mean, every time you can prove that one given algebraic manifold has a metric of constant scalar curvature, if you are not particularly unlucky, you have proved a very good theorem, because we are definitely lacking good families of examples. So I need to change slightly my question. I mean, I cannot be so arrogant to say now I want to give you a solution to this problem. So I changed the question in the following. Suppose that you start with something which has a solution, for example, Einstein or constant scalar curvature. But then in geometry, we are used to play with many geometric operations. For example, blowing up or taking Galois covers or projecting, or, I mean, when you do geometry, you do all these operations. And you might ask a more humble question. If I start with something which has a solution, does this operation preserve the solution? I mean, is the final output of this operation still a manifold with Einstein or constant scalar curvature or whatever? So for this, I think, let me start from, in fact, this is highly non-historical because this is the last theorem I proved. But I think coverings are the simplest geometric operation that a geometer does. So in this situation, I don't know if you see my cursor. If I move my cursor, can you see it? In any case, so when I drew,
yes, we can see that.
Okay, so you start, the problem is the following. You start below what I drew here as the sphere. So suppose you take a manifold for which you have a solution. So N is a manifold which you know has a constant scalar curvature or Einstein or whatever type of matrix. And then suppose you take a Galois cover of that, M. So can you actually prove that M has again an Einstein metric or a constant scalar curvature metric and so on? Of course, in the case of Riemann surface, or the only case where we can draw pictures, the answer is yes, because I showed you in the first slide the story.
Can I ask you a small question? I didn't understand. N is equal to M or G. Is there some group operating and you're looking at the orbit space or what?
Yes, that's my definition of Galois cover. So M. So this picture represents a Galois cover if I have a group acting on M with the property that M quotient the action is N. In particular, notice that it's smooth.
But I thought when you take the orbit space, it normally has singularities.
The orbit space, of course. I mean, okay. Let me stay one moment on this then. The simplest possibility, of course, of a covering is the unbranched cover. So when there are no branch points, so when the differential of the map of the projection is always non-zero. But then in that situation, of course, let me just one quick comment. This problem becomes really simple because you just take the metric below and you pull it back. And if there are no branch points, if there is no ramification, the pullback is again a metric of constant scalar curvature or Einstein or whatever you want. The problem is, as every time you have ramification, the pullback is not a metric anymore. Okay, so the problem becomes interesting when there are when there is a branch locus or there is a ramification. Depends if you want to think below or above. So the branch locus and the ramification locus are one is equal to the other modulo pi. I mean, one projects to the other, no? And so the branch locus, of course, or the ramification locus are typically singular space, singular subsets of N or M.
Mhm.
Okay, but NMM, I'm supposed they are supposed to be smooth, at least in my.
Okay. Okay.
Okay.
Mhm.
So
Okay.
you can
Thank you.
decide to ramify your cover over a very singular set. I mean, of course, in dimension one, when I'm drawing pictures, if I draw dimension one, there is not much fantasy that you can use. You can ramify only on a set of points. So, because in the complex situation, these are only ramified over complex analytic subvarieties. So there would be only ramification over points. Okay. Now, but in higher dimension, for example, if this was a picture in real dimension 4, which is complex dimension 2, is the next case, then I could prescribe, for example, a branch locus to be, I don't know, a bunch of lines intersecting, highly singular, and so on. Okay. So now, this was a situation that was studied by Tian at the end of the 90s for the Keller-Einstein problem, one specific example, and then by myself and Alessandro Chigi and Pirola in general, in the Keller-Einstein case. And now in the Keller-Einstein case, we found kind of, you see here, for example, if you want to read this theorem, you need to put, so now below it's a Keller-Einstein manifold. Above, you don't know, M, you are looking for a Keller-Einstein metric on M. And then, in fact, actually, the condition is a condition about the ramification locus. So this R of pi, here I didn't add all the definitions, but this is the ramification locus of your cover, has to be a multiple of the canonical divisor, if I were the anti-canonical divisor. And in order to preserve the Keller-Einstein metric, you did a numerical condition about the degree of the cover, which is actually the index of the group, and this homological number, so the proportionality between ramification and anti-canonical divisor. In this situation, you can preserve the Keller-Einstein metric. And actually, this was a very powerful theorem for providing many new examples of Keller-Einstein manifolds. But then recently, and I should go back here, I should go back to this development, thanks to the fact that Bernard Darvas and Lu and Chen proved that properness of the K energy is equivalent to the existence of the Keller-Einstein metric. So with Alberto della Vedova and Yalong Shi, we could actually attack the same problem. So again, this problem, and now with the constant scalar curvature metric. And we found, I think what it is presumably an optimal solution to, I mean, we found the conditions, but I won't read them. They are very technical. So I will just showing you a theorem, but I don't want even to read it. What I would like to show you is directly a couple of simple applications. Because it's quite surprising. I mean, as I said, I mean, I hope some of your young students, I mean, could take this kind of problems in their hands. I mean, just to give you the feeling that we know really very few examples. So in this construction, even by taking, so the simplest possible base space is the complex projective space. Of course, this is the prototype of, it's a homogeneous space. So this is everything. In our scheme here, this falls here. This is constant Riemann tensor, constant section, constant sectional, no, but constant Ricci, constant scalar. So it's like for a complex geometer, the complex projective space is like the sphere for a Riemannian geometer. It's the positively curved space, is the prototype of positively curved space. And even taking this very simple case with, in fact, even a very simple group action, because even with a cyclic group, if you prescribe the branch locus of your cover to be a multiple of the hyperplane section of the complex projective space, well, now let's not even read the thing. Let me just skip here. We find a very simple condition for which our theorem guarantees the existence of the constant scalar curvature metric on top. So and these were not known. So this even these very simple algebraic varieties were not known to have a complex a Kähler metric of constant scalar curvature. Okay, you can play similar games by putting as base space so every time you put something that you know has a constant scalar curvature metric or an Einstein metric, you can play with the group, the covering group, to see whether you can actually lift this metric. So for example, if you take P1 cross P1, again, you find another family of constant scalar curvature manifold, or you can even take the blow up of P2 in 3 points, which is probably the most famous Kähler-Einstein metric in the literature, besides the homogeneous spaces or similar. This was proved by Siu and by Tian Yao, the existence of this metric on the blow up of P2 at 3 points, and then you can actually play the game where your base manifold is the Siu Tian Yao metric. And again, you can keep on finding families and families of examples. I hope, as I said, I'm not entering, and this theorem is actually proved with the variational characterization that I mentioned of constant scalar curvature metric. So the way to prove this theorem was to actually check that since on the base space you have a constant scalar curvature metric, the Mabuchi energy is proper. That's one way of the theorem. Then you lift the Mabuchi energy, and then you prove that under some condition, the Mabuchi energy on top remains proper. And then by the other arrow of the theorem, you know that this implies the existence of the constant scalar curvature metric. So this is now, but in the last 5 or 6 minutes, let me mention another completely different approach to existence of constant scalar curvature metric. Now, these are called singular perturbation methods or gluing methods. It all starts with a very simple observation, of course. Every Riemannian metric locally around any smooth point, if you go sufficiently close and you look and you enlarge, of course, every Riemannian metric becomes the Euclidean metric at a sufficiently small scale. So a simple idea would be to take any Riemannian manifold, any Kähler Riemannian manifold, remove a disk, a sufficiently small disk around the point, and glue whatever you want, as long as this whatever you want as a non-compact end, how is it called, where the metric on this end becomes asymptotically Euclidean. Mathematical physicists are, I said hello before to Khalid. They are very, very familiar with this kind of situation. These are kind of metrics where gravitational instantons and so on, they are very, very much studied in general relativity and physics, theoretical physics in general. So we actually have a good bunch of these examples. If you take something like that, you can think of rescaling it down and plugging it into your base manifold near any point. Of course, when you make this operation, you cannot expect to preserve the equation that you are studying, like the constant Ricci or Ricci. In fact, the most famous situation of, in fact, the first and the most famous situation where this kind of idea was studied was the Ricci flat equation. But here I'm applying it to the constant scalar curvature equation. So you scale it down, you plug it in, but you make a mistake. In order to match exactly the metrics, you have to make a mistake. And then the question is, can you kill the mistake with kind of an implicit function theorem or something like that in order to recover an exact solution of your problem? Well, this is the situation that we have been studying actually for a long time with Frank Packard and then with Packard and Michael Singer in the case of blow-ups of smooth points. in this situation, there was available a very nice, very famous scalar flat metric with an asymptotically Euclidean end on the blow up of Cn that we could use like our local model to start this, this machine. This was called the Bern-Simanka metric. And actually, I will later show you a couple of theorems. So using this, we solved the problem of blowing up smooth points on any possible manifold. So now much more a project that is going on. I wanted to mention because, as I said, my student from my Pakistani student, Samrina is involved, and again with Frank Packard. We are finishing another project where the model that we introduce inside the manifold now is known as two ends. On one hand, it has to be asymptotically Euclidean, and this we need in order for this procedure to start, in order to fit it into any manifold. But actually, it has also another end, which looks like a cusp in some sense. But the strange thing is that typically cusps in geometry, you think of the word cusp and you think of negative curvature. This is actually a space of zero curvature. And it has been found by Fu, Yao, and Zhu a few years ago. So using this model, we are now writing down. So there are two outputs of this construction that I was involved with. One is take any Kähler manifold of constant scalar curvature, take a bunch of points and blow up. And this is what we did with Frank Packard. And we showed the existence of constant scalar curvature Kähler metrics in this, at least for very small volume of the exceptional divisor. You have to think of this, you are creating a bubble, and for a small volume of this bubble, the theorem applies. And now with, again, Frank Packard and Samrina, we are inserting this kind of strange cusps around every point. So in particular, even if we start from a constant scalar, a compact manifold, the output of this machine will give non-compact manifolds, but with this prescribed ends behavior at the ends. Okay, I hope this will be finished around Christmas. I mean, I hope the Christmas break will be the critical break to finish the paper. So for blow-ups, let me just mention another possible way to visualize what we have been doing. The moral is, remember when I told you at the beginning that the linearized, when I studied the equation by PDE methods, I mentioned what is the linearized operator. And the linearized operator is this Lick-Nerowitz operator. And I told you the kernel of this operator actually is the space of holomorphic vector field. So now this is a situation where so when I said, okay, we gave the picture of when you can blow up points, and the moral is if your base manifold has no holomorphic vector fields, basically you can do whatever you want. And this is thanks to what I said before. So the linearized operator is invertible in that situation, and this hugely simplifies the proof of the existence of the constant scalar curvature metric. On the other hand, if your base manifold has holomorphic vector fields, so which is actually strange if you noticed, holomorphic vector, the existence of holomorphic vector fields for a geometer is good news in general. I mean, this is maybe just philosophy more than mathematics, but as I said at the beginning, a geometer likes isometries, likes transformation. I mean, a space which can be deformed by itself, I mean, is supposed to be nicer. I mean, you think that the sphere is the nicest space because in fact you can do all sorts of transformation and you stay on the sphere. It has the largest possible isometry groups. Now, for this problem, the existence of continuous holomorphic transformations is actually a problem and gives obstructions. So if there are no, you can do whatever you want. If there are, Well, again, I won't read this statement. This is the statement of my theorem with Franck-Paccard in the case of holomorphic vector fields. But the point is, what I would like you just to get as a message, you can actually blow up points, but only if these points are put in a very symmetric position. And actually, this is very much inspired by similar theorems that people, like, for example, Nikos Kapouleas has proved in the 90s and keeps on proving now about the existence of constant mean curvature surfaces in R3. There is a very neat analogy between this kind of global abstract problem about algebraic manifolds and constant mean curvature or minimal surfaces in R3 or in Rn, which I think actually adds some beauty to this kind of problems and techniques. But also in this situation, you see, for example, if you want to construct out of one constant mean curvature surface something else by taking bubbles, by doing bubbles, and the problem is that you can do it only if the bubbles somehow balance themselves. Okay, a bubble gives some kind of force to move everything in one direction. And so there should be another bubble opposite to that, which kind of rebalance this force somewhere else in the opposite direction. So this is a situation which is now, I mean, kind of present in many geometrical problems when you want to do this kind of singular perturbation. And this appeared very neatly also in the blow-up problem. Okay, so I think I could stop here, and I want to thank you again for your attention. Sorry about the technical problem.
Yeah. Thank you, Professor Arezzo. Any questions from the audience?
Yeah, I have a very general question. So, Professor, all this line of research, I mean, does it tell us any topological things about the manifold, or are these questions interesting in themselves? It's a very general question.
Okay, no, that's very important, of course. So, why? I mean, why are we interested? Well, I hope I convinced you that there is a general philosophical interest about finding the best metric. But on the other hand, you are absolutely right. I said finding the best metric is a beautiful problem, because if there is a best metric, presumably this metric remembers something about the underlying space.
Mm-hmm.
Now, for Keller-Einstein, so remember in my staircase, now if you go down, so of course, if you have a constant Riemann, well, of course, the existence of the constant Riemann metric, of course, tells you a huge thing about the space itself, but this is kind of a consequence about the fact that there are only 6. So you can actually have a list and check. Constant sectional, again, constant sectional becomes a quotient of the model. And so, and also in the case of complex or Keller, you would say holomorphic sectional, which is a weaker condition, and still you get as a conclusion that that your space has to be a quotient of complex projective space, Euclidean space, or the complex hyperbolic.
I see.
Mode. Okay.
So there's some classification associated with all of these things, huh?
Yes, but I would like to be honest with you, because it's certainly true for Riemann, for sectional. Something you can say about Keller-Einstein. So if you prove that your manifold is Keller-Einstein, you can actually get a lot of information also about the topology. Not too much, I mean, not an exact classification, but you can actually get many geometric information on the underlying space. For scalar, this is not true. For Scala, this is not true. So the reason to try to prove as much, I mean, that as many as possible manifolds have constant scalar curvature comes from another source of problems. It's not inconceivable, let's say. This would be the kind of the second step in all this very long program. If Tian, Yao, Donaldson are correct, the existence of all these metrics is equivalent to some form of stability. I told you this is proved in the Keller-Einstein case. It's possible, it's likely true also in the constant scalar curvature case, but it is still not known. If it is true, then this should allow geometers to construct moduli spaces. I mean, there is a big problem in geometry about studying families of manifolds with some kind of with something in common, and this could be one of the main applications of the existence of constant scalar curvature, Keller metrics. Okay.
I see. Okay.
On the other hand, on the other hand, you see, we cannot hope for a classification. I mean, if we go down too much, we cannot hope for the classification because somehow we don't want the classification. I mean, we are trying to construct the best metric on any possible manifold. So we cannot expect that there is a classification at every step. Otherwise, in some sense, we chose to leave the classification problem in order to get something else. And you see, this kind of construction of moduli space, I think, again, everything boils down to this picture. If you know, here, of course, I told you only on any Riemann surface, there exists a unique constant curvature metric. But as you probably know by the questions that you are asking, it's clear that you know that actually is the beginning of a story. And the story is Teichmüller theory. I mean, you want to move, you want to study all together these metrics. For example, you fix a topology, the genus, and you want to study all Riemann surface of genus 5. And you can do it in many ways. And one way is to study all the set of hyperbolic metrics on topological surfaces of genus 5 altogether. So here, the dream is to do this in a higher dimension. So you prove existence of special metrics because you hope to be able to study families of manifolds with associated families of metrics, and then presumably to study, like we did in Teichmüller theory, study degeneration, compactifications of this moduli space.
I see. Okay. Okay. Thank you very much. No, and one more small question. All these flag manifolds are Keller-Einstein. So does the existence of this special metric tell us anything about the flag manifold itself, or it's just a curiosity?
No, well, I'm not an expert on so I would not dare to make a very bold statement. You see, geometers tend to be, you see, even in the most famous sectional curvature situation, you see, for a geometer, you say, if your manifold has constant sectional curvature, for example, suppose it's positive, you say it's the quotient of a sphere.
Yeah.
And then you say, a geometer actually a little bit snobbish, say, okay, and for me it's over. That's the problem is solved. But actually, if you think a bit better, the problem is not solved. I mean, okay, so which quotients exist of the sphere? It becomes more an algebraic problem. It becomes more how many groups inside the isometries of the sphere, but it's far from trivial.
Yes.
I think what you are referring to is kind of, again, once you prove that your manifold is a flag manifold, in some sense, for a purely Riemannian geometer, as I must confess I am, In some sense, the
Everything
problem is over.
is over. Yeah, yeah,
But-
yeah.
but-
You know,
But it's
yeah.
not over at all. It's just it's not fair, because actually you enter more the algebraic side of the story, and it remains very interesting.
Mhm. Okay.
And very
Thank you very
difficult.
much. Yeah,
And very
thank you very
difficult,
much.
actually. So
Yeah. Thank you, Hassan. Thank you, Professor Arezzo. Any other question from the audience?
Yeah,
Yeah.
Arezzo, thank you very much for this nice talk. This concept of asymptotic flatness, that plays a very important role in mathematical physics. So you mentioned also in your talk. So does this have any analogy in the more general case, or in these Keller manifolds?
well, this idea, in fact, actually is due to Page, no, a famous physicist from.
Yes, yeah.
So Ricci flat, for mathematical physicists, Ricci flat is by far the most interesting equation. So would be the Einstein equation in the vacuum. So and actually physicists came first, and then mathematicians followed up, you know. And this type of construction was proposed, was not proved, because actually the proof became quite sophisticated, but was proposed by Page in order to construct the first compact, non-flat manifolds that we knew, that like the K3 surfaces were called. You see, up to the end of the 70s, all the examples of Ricci flat metrics that we knew were actually flat, like flat tori or Euclidean space and so on. So then what Page proposed was actually to take a 4 torus quotient by a group, and then play this game to resolve this thing with another metric. In this case, you see, you need a model. In his case, the model he proposed was the Eguchi-Anson metric, which is another famous metric in this Ricci flat discovered by physicists.
Yes. Yeah.
And in this way, he proposed to construct what is now called the Kummer K3 surface with a metric. The idea was fantastic. It was proved to work only 20 years later, no, 15 years later, by Topinvala, Lebrun, and Singer. And then since then, yes, I mean, the problem is the only gluing technique, well, now this is a bit of a bold statement, but this technique applied to the Ricci curvature, basically it works only for the Ricci flat equation. So if you want to construct a positively Ricci curved or negatively Ricci curved, this might not be a great idea. But,
Okay, so not in general case, yeah.
But Ricci flat, it works very well.
Yes. Yeah.
And now, I mean, yes, my contribution was to extend this idea to the constant curvature equation.
Yes. Okay. Thank you.
Okay, Professor Arezzo, I have some very basic question. Please pardon me for very simple question. May you please elaborate, what do you mean by polarized variety?
Polarized variety. No, polarized, sorry. This, yes, this was a little bit of a jump here. I just wanted to, a polarized variety, look, everything, now I don't want to take too much time, but remember, a Keller metric has a very special feature. A Keller metric gives a closed 2 form. So this omega, so by the metric and the complex structure, you construct a 2 form. Now this 2 form turns out, because it's closed, actually it's never written here. The Keller condition, you can say is nabla j equal to 0, but it's equivalent to d omega equal to 0. Now, d omega equal to 0 means that omega represents a 2 cohomology class. And in particular, you can go and check, this is a class of type 1, it's real, and so on, and positive. So when, 1 classes, I mean, among 1 classes, there are the first Chern classes of line bundles over complex manifolds. So not every class is the first Chern class of a line bundle, but first Chern class of line bundles are always there. So now polarized means that you are actually studying a manifold with a line bundle, meaning that you are looking for metrics in the first Chern class of this line bundle. So of course, in particular, this line bundle has to be ample. In the language of algebraic geometry, ample means that the first Chern class is positive. Because if you want this bundle to, if you want the first Chern class to be represented by omega, and omega comes from a metric, the metric is positive definite, omega has to be positive definite, and so the first Chern class of L has to be positive definite. This is the notion of ampleness of line bundle. So a polarized variety, basically every time your algebraic variety is inside one projective space, you automatically have it polarized, because so basically L is the line bundle whose sections gives you the embedding in the projective space. It's a particular class of classes, of Kähler classes on an algebraic variety.
Okay. And may I ask one reason where you was explaining about the cross-sectional area and gluing, and all the manifolds under discussion are orientable.
Sorry, can you repeat? I didn't hear well.
So any specific purpose of keeping everything orientable?
Yes, there is. Yes, there is a reason for that. But now let me think. Yeah, if your manifold is not orientable, it does not even have a complex structure. So complex manifolds are orientable.
Okay. Okay. Thank you. Any other questions from? Thank you very much, Professor Arezzo, for your answers. Any other question from the audience? Okay. If this is the case, let us thank Professor Arezzo for a wonderful talk and a very elaborative one. And I hope many students and many people benefited from it. And thank you, Hassan and Khalid Saifullah, and thank you.
It was a pleasure, and thank you, Professor Arezzo. Hope to see more of you in these seminars.
It was my pleasure. It was my pleasure, and let's hope we can meet soon in Lahore.
In Lahore, inshallah. Yes.
I hope in near future. Khalid, safe travel. Safe travel.
Okay. Thank you very much. Yeah.
Thank you, everyone. Thank you. I hope the next seminar week after the next week is by Professor Eddie Laptev about the operator theory from Imperial College London.
Okay.
See you all till then. Thank you, Professor Arezzo. Thank you, everyone.
Bye.
Bye-bye.
Okay. Bye-bye.
Yeah.
Bye.